density, and calculating with density is what we would consider an intensive property. What's an intensive property? Doesn't depend on the mass. Doesn't depend on the amount of matter you have. So density of water is the same whether we have 1 molecule of water or 1,000,000 molecules of water. Right? Same for all substances. The density of an object is the same no matter what. Okay? Regardless of the size, the density should always be the same. Yeah, William? Good. Density equals mass divided by volume. So D equals M over V. Okay, we talked about what units for density usually look like. Do you remember what they are? That was in your lesson last time. If we just think about it a little bit. Mass and volume units. Grams per centimeters cubed, okay, or grams per milliliter. What do we know about a cubic centimeter and a milliliter? They're the same. A cubic centimeter and a milliliter are the same. So if you wrote that down in your notes last time, make sure you star that or highlight it or write it down again if you don't have it. But 1 milliliter is equal to 1 centimeter cubed. Right? A cubic unit is a volume unit, right? If I find the volume of a cube, how do I do that? Yeah, length times width times height. So I take a length times a length times a length, right? So that's a cubic unit. So any cubic unit is a volume unit. This is an easy connector for us to go from a volume in cubic centimeters to a volume in milliliters or liters or kiloliters or whatever it is. Okay, so you probably had a couple questions on your homework that had to do with connecting centimeters cubed and liters, right? This was your big conversion between those two, okay, because 10 milliliters is equal to 10 cubic centimeters and vice versa, okay? Is how compact these molecules are, how much space is between these molecules, how dense, right? We shouldn't use the word dense in the definition of density, right? But it's essentially telling us how compact these things are. Okay, so something is really dense, such as, what's an example of a really dense substance? Lead, rock, right? Things that are, usually we consider dense to be more dense than water, right? If it sinks, we would consider it dense. If it's light, we would consider it, floating on water or whatever. Okay, so something dense, the atoms are more compact, they're closer together. If something's not very dense, the atoms are a little bit farther apart. Okay, so how compact things are. All right, so let's try this one. Calculate the density of an object that weighs 16 grams and has a volume of 0.35 centimeters cubed. Okay, so knowing what I know about that equation, I want everybody plugging that in. If I know mass over volume, all right, somebody raise your hand and tell me what you got. Yeah, Logan. 45.7. 45.7, good. And what's our units here? Think about what our units were given in, grams and centimeters cubed. Okay, look, all we did was take 16 grams divided by 35 centimeters cubed. So our units are exactly that, grams divided by centimeters cubed. Units are really important, so keep those throughout the whole thing. Grams divided by centimeters cubed, that's our final answer. Okay. There's no need for us to change it to milliliters, even though we know it's the same thing. Right? There's no need for us to change it if we're given in centimeters cubed. Questions there? Okay. Oops. If a certain compound has a density of 3.21 grams per milliliter, if I have 24.8 grams of the substance, what's the volume? when we're trying to solve for volume, the bottom, or something in the denominator, we switch these two places. Okay, so whenever the variable that we're looking for is in the bottom of one of these triangle type, okay, right, this is what I would consider a triangle type equation. Whenever what we're looking for is in the denominator, we switch those two places. So essentially we're taking 24.8 divided by 3.21 to get our volume. Okay, so I got about 7.73. Would we agree with that? What would our units be? Milliliters, good. It has to agree with our density units. Okay, so 7.73 milliliters. Try the bottom one here on your own. There should be something that sticks out to you here. Liters. We can't use liters because our density is given in grams per milliliter. So this has to be converted before you can use it. Convert to milliliters. Okay, so please make sure you do that. And if I want to go from liters to milliliters, what should I do? Multiply by 1,000. Good, right? We should have a lot of milliliters contained in 0.32 liters. So you should end up with a bigger number there. Good, and what's our units for that? Grams, perfect. Our next little topic, chapter 2, has a couple different things, and they have to do with us expressing measurements. So we talked about units for measurements. Density is kind of thrown in there, but whatever, we're pretty familiar with density. And now we talk about what's the correct way to express a measurement in terms of the amount of digits we represent. Okay, and these are called significant figures. Okay, and significant figures is probably a totally new concept to you, and that's okay. Right? So what significant figures do, they allow us to understand what digits in a measurement are important or considered significant. Okay, so not every single digit given in a measurement is what we would consider significant. Okay, so I'm going to give you some rules to determine how we know that digits in a measurement are significant or important. Okay? Okay, so for example, you don't have to write down the example, you can just listen if you want. We have a meter stick that's measured to measure this pen, okay, and it says it's 14.3 centimeters. Anytime we make a measurement, what do? Right, when we use an instrument to measure something, how do we read it? Do you remember that rule we talked about? You read what it gives you, then what do you do on the last one? You estimate one more. Okay, you read what it gives you and you estimate one more. So that means this meter stick was measured to the whole number, the whole centimeter, and then they estimated that decimal, right? They thought the pen was somewhere between 14 and 15 centimeters. Does that make sense? So this measurement would be considered what we have, it would be considered to have 3 valid digits. 2 that we know for sure and 1 that we estimated. Okay, so that would be considered 3 significant figures. Okay? 2 that we're sure of, and 1 that we estimated. Okay? So I'm going to give you some more rules for significant figures, and we'll do lots of practice with this. But these are telling us what digits in a measurement are considered important, are valid, right? What do we know that's happening in a measurement? Any value that's given with non-zero digits, okay, or all non-zero digits are considered significant. Zeros are where things get fuzzy. Okay, but any digit that's not a zero is considered significant in a measurement because we read it, right? We don't just make up zeros or make up sevens and add them to an end of a measurement for no reason, right? We think there was a 7 there or whatever it happens to be. So all non-zero digits are significant. All zeros to the right of digits after the decimal point are considered significant. Okay, so write that down and then think about what that would look like. So let's say these were 3 measurements that we have taken, right? These are measurements from 3 different groups. They were measuring something 4 centimeters long. Okay, which of those is the most exact measurement? First, second, or third? The third, right? Because it's got 2 decimal places. That means we read that one, and then we estimated the very last one. So both of these zeros, since they're to the right of digits, after the decimal point are significant. And that's because we are saying it's exactly 4.00. Right? That's what we think. We think when we measured it, it was exactly 4.00. Okay? So how many significant figures does this number have? It has 3. Right? So how many sig figs does this number have? 2, and this one has 1. Right? So we see the more significant figures we have, the more of an exact measurement we have. Okay? And it's all about what your instrument gives you. So you can't always just say, oh, each measurement is 5 sig figs, right? That's not how it works. Every instrument is different, so it depends on how you can read your instrument. Okay? Okay, so what we're saying is we could put the number in scientific notation to help us better describe that number. So zeros to the left of digits are non-significant. They're placeholders. Question. All non-zero digits, so for sure 1 and 2. Zeros to the right of digits after the decimal point are significant. Zeros to the left of digits are non-significant. Okay, so 3 sig figs. Okay, all digits used in scientific notation are considered significant. All digits in scientific notation are significant. So 2.47 times 10 to the 14th. How many sig figs do we see here? Any ideas? Just the visible digits in scientific notation. 1, 2, 3. Okay, that's it. We don't care about the 14 extra zeros tacked on the end. Right? We care about the numbers that are visible here because these are the important ones. Okay, scientific notation allows us a lot of flexibility with significant figures. Okay, because we can take as many as we want in scientific notation. That's always going to be a way that we can fix a number in scientific or for significant figures. Okay? Questions so far? I know this seems really abstract and really different, but any main questions yet? We're going to talk about Thomas's question here in a second. Okay. Some numbers are considered ambiguous. We don't know how many significant figures there are, which means we don't know if the measurement is exact or not. Right? That's what we're looking at here. We don't know if our measurement is exact or if it's not. So here's what makes a number ambiguous. See these zeros on the end? No decimal place, no scientific notation. These are what I call trailing zeros. Scientific notation will work every single time, all the time, no matter how many significant figures you are allowed. Because you can fix scientific notation to look however you want. Decimal places are a little bit trickier. So when we talk, yeah, sorry, Sam. So the reason I'm talking about fixing numbers is because there's rules for how you add and subtract digits and multiply and divide digits with significant figures. Okay, so we're going to talk about that. You're only allowed so many significant figures, depending on what measurements you have. So this is why I'm talking about why you fix them. Okay, I'm going to show you how we do it, but I'm telling you this is why we do it. Okay? So if I had the number 120,000 and I was only allowed to use 3 significant figures, how could I fix that? If I had to put 120,000 into something to show me 3 sig figs, how could I do it? Yeah, Annalisa. 1.20 times 10 to the 1, 2, 3, 4, 5. Right? Perfect. Perfect, perfect. Okay? 1, 2, 3 significant figures. Okay? If I had to fix it so I had 7 significant figures, how could I do that? If I was allowed 7 significant figures, how could I do that? Yeah. Yeah. 120,000.0. Okay, that then turns all of these digits significant. So adding a decimal place therefore lends another 0 at the end. So I'll see some people do this. 120,000 and then point. Right? That has to have a 0 after, which makes it 7 sig figs. So if we need 6, people will do that. Right? We added a decimal place. Okay, but a decimal place automatically lends itself to something following that. Okay, so if you need 6, you got to put it in scientific notation because there's no way you can do 6 without an extra 0 on the end. Does that make sense? This is 7. Sorry. Some people would say, like, oh, if we only allowed 6 sig figs, they would do this. Right? Which doesn't work because that has to be a 0, which would then make it 7 sig figs. Does that make sense? Yeah. Okay. Questions? What'd you say? 1.20 times 10 to the 5th, right? 1.20. We moved the decimal place 1, 2, 3, 4, 5 to get it between 1 and 10. So that's why it's 10 to the 5th. And it's 10 to the positive 5th because 120,000 is bigger than 10, right? The number we're trying to express is bigger than 10, so our exponent is positive. All right, what questions do we have so far? Okay. Okay, so now we get into the part of the class where the math we do has to be significant figure oriented. Okay, so you have to take significant figures into account, or sig figs. So there's more rules. Like today's all about rules. When you're adding and subtracting measurements, you add and subtract just like normal, and then you round your number, you round your answer to the least precise value involved. Least precise value involved. So what that really means to us is round to least number of decimal places. Okay, least precise number involved. So the reason we do this is you can't have an answer that is more precise than one of your measurements. Okay? Your answer can only be as precise as your least precise measurement. Okay? So if I'm doing all these things, I have 4.2 centimeters plus 6 centimeters plus 2.18 centimeters. I'm going to do all that math, okay, and I'll even do it for you. We're adding and subtracting here, so 4.2 plus 6 plus 2.18 gives us a raw answer of 12.38. So my answer, is it more precise than one of my measurements? Yes, which is not allowed, right? So I look at each of my values. This has how many decimal places? 1. This has how many decimal places? 0. This has how many? So I have to round my answer to my least precise number of decimal places, which means I have to round to a whole number. Okay, so this is my actual answer there, 12 centimeters. Which stinks, right? We think we want our measurements to be as precise as possible, but we must have slacked on that middle measurement. Okay, if we thought it was exactly 6.0, we should have measured it to 6.0. Right? That would have allowed our answer to be a lot more precise than it really is. Okay, so your answer can only be as precise as your least precise measurement. So adding and subtracting, you're not really even thinking about sig figs, you're thinking about decimal places. Okay? Questions? Okay. So look at this problem again. I gave you this another one. I did the math for you. 12.520 plus 14.0 gives me 26.520. Does my answer have the correct number of sig figs? No. So what should my actual answer be? 26.5. Oops, I didn't write it up there. Here's something else we need to think about. What if it came out to 26.580? What would be my one decimal place then? It would be a 26.6. So you're not only thinking about putting those decimal places in the right number of decimal places, but you got to think about rounding that decimal place the right way. Okay. So a 5 rounds up, 4 under rounds down. Yep. All right. So I did the math for you here. 2.40 times 12 gives us a raw answer of 28.8. So let's count sig figs, right? We're not thinking about decimal places anymore. We're back to sig figs. So this 2.40 has how many? 3. 1, 2, 3. This 0 is to the right of digits after the decimal point. So this has 3. How many does 12 have? 2. Is 12 ambiguous? No. There's no trailing zeros, right? Those are both non-zero digits, both significant. So our answer has to have 2 sig figs. How can we make that happen? Just round up to 29, right? That works fine. If our answer is ambiguous, oh, you go to the least precise that you know. Good question. Ethan asked the question, what if one of the numbers in our math problem was ambiguous? We would just go to the least that we know, right? We'd go look to another number that's not ambiguous, and we'd go with the least number of sig figs that we know. That was a good question. What would be another way we could express this with 2 sig figs? Yeah, 2.9 times 10 to the first. Right? You could do that. That's a little bit like extra. You don't need to do really when it's 10 to the first, but you could. Right? Scientific notation will always work. Okay? How are we feeling? I know this is a little like crazy, right? It's all new. So just make sure you ask questions if you have them. Let's try some here. So raw answer here, I got 319.7. Agreed? How many sig figs can our answer have? 2. Has to round to the least number of sig figs given. This one only has 2. So how do we do that? Scientific notation. Does this work? No, because what's wrong with this number? It's ambiguous, right? That would get you like a frowny face on your paper if you give me ambiguous numbers. Okay, so don't do it. So the way we fix that is we go to scientific notation. So here's what our options are. 3.1 times 10 to the second or 3.2 times 10 to the second. Which is our better option? 0.2, right? Because 319 is much closer to 320 than it is to 310, right? So here's our final answer. 3.2 times 10 to the second, and our units here would technically be centimeters squared. Okay, so do we understand why we had to go to scientific notation? How many of you wanted to give me the answer 320? Right, that's okay, but no. Don't do it, okay? No ambiguous numbers. The way we fix ambiguous is scientific notation almost 100% of the time, okay? All right, try this one on your own. I think you can do it on your own. Okay, this number is between 1 and 10. This exponent is positive if the number we're trying to express is greater than 10. It's negative if the number we're trying to express is less than 1. Okay, so scientific notation is a way for us to express really big and really small numbers. That's what it's used for. Okay? And we try to, for some reason, somewhere along the way, you guys tried to memorize, oh, if I move the decimal to the left, it's this. If I move the decimal to the right, it's this. That's no good. Okay? It's no good. If the number we're trying to express is greater than 10, our exponent is positive. If the number we're trying to express is less than 1, it's negative. That's it. Okay? That's all I'm going to tell you about scientific notation. We're not going to go into how to do math with scientific notation because you have a calculator. I'm not going to make you do math by hand with scientific notation. That's silly. Okay?